Did you write down what I asked you to write down yesterday?
Oh, no.
What did I tell you to write down yesterday? Somewhere, anywhere. Nobody?
I did.
Extra. What did I have you write down when it came to this section yesterday? Baby tangent. Thank you. There it is. Baby tangent. Yesterday, period 6 was talking about Baby Yoda. I don't know. Whatever you want to think about. Baby tangents. Now, question. Did anybody go up to Lancaster or up there in the Palmdale area to go see the poppy fields? Okay. So, when I tell you to envision a field of poppies, what are you envisioning?
Bunch of orange colors.
Bunch of orange colors? So I can just stick a basketball in front of your face and it's a poppy field? Be specific.
Hills full of flowers on the floor.
Nice. Fields full of flowers. Yes, like a wide open space with lots of flowers, right?
40-mile-per-hour wind.
Yeah, so much wind.
It's my living.
So, field, like a space, right? A space, and a poppy field, like if it's good poppy fields, and if they're in bloom, then you should see all kinds of, maybe you don't know what a poppy is, all kinds of flowers.
Bees.
This used to go all the way across.
Oh.
And then that part broke, and then that part just...
They're gonna fix it, Misty. They're gonna fix it.
The last part. Bummer is, there's gonna be a screw that's gonna like totally jam into me. Anyway, that's alright.
I'm getting wood glue.
We're all falling apart here. Literally, I have a string. Anyway, so, fields of poppies, a space, an area, a region that is full of flowers. Now, literally full of flowers? Like full, and you can't even see green? No, I mean, good poppy fields, there are a lot of them. But not literally like completely packed, more of just like interspersed throughout. So when I say slope fields, and if I told you yesterday to think of the slopes as baby tangents, wait a minute, how do we get slopes of tangents?
Derived.
From the derivative. Wait a minute, and who is the derivative? What's a snazzy name for a derivative function or equation? And what's it called? Differential equation. So, baby tangents, slopes of tangents are found by derivatives. Derivatives, snazzy name, differential equations, right? Equations of derivative functions. Or they could be functions or in terms of x. Could be in terms of x and y and be like an implicitly derived one. Does it kind of make sense, the pictures I showed you at the very end of yesterday, that there are, well, those ones haven't been made yet. Those are just fields. Those are just areas or regions on a graph that need to be made. Ooh. But do you see how it's an area, it's a region that's filled with little baby tangents? Tangents normally go on forever, right? But we're taking little baby slivers of them. Little baby slivers. And yesterday, Adam, how did you say, wait a minute, is that sun?
I think I was wrong. But it kind of just looks like a sine wave.
Exactly, because the little baby tangents are kind of showing us the flow of a function that's going through. And we didn't get to actually write all of that yesterday per se, but if we put together a field, a region of little baby tangents, and technically, guys, like mathematically, we didn't have to just put a tangent here and here. We could have put one there and there and there. We could have completely packed this with tangent lines. But if it was completely packed, if it wasn't like interspersed, I don't know, I think you probably still would be able to see what was going on because you would still have like this movement. But we don't have to make tons and tons and tons of baby tangents. We just need some interspersed throughout this entire region to follow the flow. Adam, you were totally correct in that this is letter F. Hey, you guys have a packet in front of you. Question, was example number 4, is that in that packet? Is that where these are coming from? So can't we label number 1 as F? Now, there's some stuff to see before that, but I'm just showing you where we are and where these examples are. Because for you guys to draw this in your notes would be super tedious, super annoying. We are going to fill in some things in our notes. However, a lot of slope fields are going to come from the packet just because it's going to be kind of hard to like write all these down for examples. It's a lot easier if you have a copy. Kathleen? Oh, Mary, hand this up, sorry. And Adam. Just because of the zoom. So if you look back at, and you can look in your packet too, you see these ones with little dots? We could technically find the slope at 0, 0, and at 0, 0.1, 0.2, 0.3, 0.4, and we could find it at, let's see, where are we at? 1. We could also find it at 1/2. Think over here. Doesn't sine level out at something awkward decimal-ish, right? Doesn't sine level out at pi over 2, and pi over 2 is 3.1415926 over 2? Unless this slope field was generated by going from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi, you're not going to see those nice little leveling off areas. This slope field is probably generated with 0 and 1 and 2 and 3. Yeah, probably 0, 1, because pi over 2 would be a little bit more than 1, so see, Kathleen, we kind of just have to follow the flow and realize if we have an upward slope and a downward slope, and if this is out of a continuous function, there's going to be that leveling off at that awkward 1.5-ish in between. Does that make sense? So remember, when you're looking at these slope fields, you're not seeing literally everything. If you were seeing everything, these tangents would just be like little baby slivers that wouldn't even still be everything. But you would have this path to be basically solid with lines, and it would be completely joined or connected. So we're just kind of remember, we're just doing interspersing of. And if you guys notice, that kind of makes our life a lot easier, because how many baby tangents, guys, would we need to put in this example number 3? How many? How many will we need to put if we're making a slope field and if they've given us just that? There are infinitely many that can fit, that how many are we going to make? We got 6. It's a 3 by 3. 9. Yeah, we're just going to do, and this one, how many slopes are we going to have to do? 1, 2, 3, 4, 5, 5, 5, 1, 2, 3, 4, 7, 35? Now some of you are like, I have to find 35 tangent lines?
Wait, so they go through the dots.
So think about these dots as being the locations of the individual interspersed slopes. This one's really nice. This would be like an example part A on an FRQ. Part A could be like, hey, make a slope field from this differential equation. Wait, how is this a differential equation? It's not dy dx, but what is it? It's y prime. Could it be written as dy dx?
Yeah.
Okay, so it's a derivative. It's a differential equation. This is funny. Why? Because it has x's and y's. So didn't we learn last semester that you can take derivatives of x's and y's? We can have an implicitly defined derivative. Anyway, we're going to make some slope fields, but first, can we go back to a couple things we're going to do in our notes? Have that packet open and ready. We're going to be doing examples from there. But before we do that, let's take a few things in our notes. One of which is, let's start at the very, very, very foundation of differential equations. This is kind of where the Beasley book starts with differential equations. Your book maybe just a little bit, but not a lot. We're trying to expose you to the idea that there are harder differential equations than you've seen before. Why or how, as you guys are writing this guy down, why or how is he a differential equation? We just saw one. You just answered for that one. So how is this one a differential equation? We just talked about how every differential equation does not literally need a dy over dx. There are other notations. What do you see in this that makes it a differential equation?
It says
True, but what do you see in it? I'll give you a hint. This isn't just any differential equation. This is technically called a second order differential equation. Some people affectionately or not so affectionately call it in college DPQ. A second order differential equation. DPQ, they actually spell it DIF. And then DPQ, EQU. What do you see in there that makes a differential equation? Differential equation says it has to involve what? Oh, we haven't gotten it yet. Derivatives. It has to involve derivatives. Does this have derivatives? Yes.
Yes.
Specifically, what kind of derivative?
double.
A double derivative, or also known as a second derivative. So why is it called a second order differential equation?
It's not the first order.
Because it involves a second derivative. Now hold on, guys. Why do we call a quadratic if it has like a linear x in it? Why do we call it quadratic degree
Where?
2? Because the highest degree is a 2. So a cubic, the highest degree is a 3. Could it have a square and could it have a single? Sure. But we name differential equations similarly to how we name polynomials. We name it according to the highest derivative involved. Wait, the highest derivative, so do differential equations only have y primes? Oh, they can have y double primes or y triple primes. Differential equations just mean equations that involve derivatives. Okay? But we're not going to really see any of these higher order differential equations. Oh, that was weird. Because we're not going to see a lot of them with double primes or triple primes just because of the level of math that we're in. We're just dealing mostly with single order, which means like a y prime, single order differential equations. But the book might ask you to do something with a harder differential equation. And this one, they're not actually asking you to solve. Do you see this saying, or do you see it directing you at all to solving this differential equation?
No.
With an integral? No. What's it saying? Yeah. Very similar wording was given to pre-cal when we started systems of equations and they gave them a point at x, y, and said, hey, is this a solution of the system? Were they saying to solve the system or just to check? Just to check. And how do you check if something's a solution of a system? Plug it in, and see if it works. And if it doesn't work, well, it can't be a solution. So what do you think this one is saying when it says determine if it's a solution? Plug it in. But how do we plug it in? We need y double prime. Find y double prime. All right, ready, set? Find the y double primes, plug it in. Find the second derivative, subtract the original. Which one or ones equal 0? 1 or 1s equal 0. Which one or 1s equal 0?
Oh, no.
In order for that to work, doesn't the y double prime have to equal the exact same thing as the original?
Yes.
Which one or ones will the y double prime equal the same thing as the original? Ooh, this is like the bonus last semester on that test.
Wait, is there a one?
Yes or no?
No, there could be one. Because it's saying is A, is B, is C. 3 separate questions. On the bonus last semester, it was which of the following does dy dx equal, I forget exactly what it was. But you had like a Roman numeral 1, Roman numeral 2, Roman numeral 3, and it could have been 1 and 2, 1 and 3, 1, 2, and 3, and 1. I just made up those answers. It was something. Why is letter A a no?
Because negative
Sign minus negative sign is going to be 2 sign. No, that's not 0. What was the first derivative of 4e to the u? 4e to the negative x? Why is it negative 4e to the negative x? U prime. Good. Nice. 4e to the u times u prime. Do it again.
Did we do it again? Yes.
Why is that good? Letter B is a check, because if I subtract them, they're the exact same thing. How about letter C?
Yeah.
Yes. Because this guy's going to always be the same, right? Okay. So can we deal with harder differential equations? I mean, I guess, if they just want us to check. But don't worry, you're not going to be solving. And to be honest, we're going to see in chapter 5, remember the whole chapter is called differential equations. We're going to see ones that we cannot solve by hand. And so if we ever see something crazy, and I'll show you a few examples as we go on. Something crazy in like an AP FRQ and it's a differential equation, we have to make sure that we read the directions very carefully. And if they say to solve or to find, then okay, maybe. Then maybe we're actually tackling it and trying to take like integrals to go backwards. But otherwise, they could be using wording where you were never supposed to solve. You were supposed to just use it, analyze it, check it, things like that. So anyway, all this is to say, if I had just thrown this up at the screen at the beginning of the class, maybe I should have and told you guys to go. Some of you would have thought, I don't know, I think I'd have to take integrals. But according to the wording, all we have to do is check. Solutions. Solutions to differential equations. Each of these were potential solutions. These two ended up being solutions. What are solutions to differential equations? Given some equation with derivatives, the solution is Are these derivatives? No. So what are solutions to differential equations? They are the original.
Oh, geez.
Now, this could have like a first derivative, second derivative, third derivative, I don't know, but somehow differential equations always involve rates. Rates of rates, rates of rates of rates, if it's a third derivative, rates of rates of rates of rates, if it's a fourth derivative. Anyway, differential equations involve rates. Maybe the original also, but they involve rates somehow. Solutions say, oh, let's go back to the amount. Let's go back to the original. Does that kind of make sense? But these ones, we weren't solving for the solution. We were just matching the possible solutions. So let's talk about solutions for a second. General solutions. General solutions. For general solutions, we could be asked to, actually for all of these, we could be asked to do a few different things. We could be asked to check that they're solutions like we just did. We could be asked to somehow use whatever the solution is, or we could be asked to find. And usually with find, they put something like y equals f of x. We could be asked to check it to see if it is a solution, or which of the following are solutions. Could just be checking. We could be asked to use a differential equation or use a solution, even if we're not. I should just stop there. To use it, or number 3, we could be asked to find it. And if it's finding, that's the only one where we're actually solving. Now, when we solve, what are we looking for? In general, we are, or with the general solution, we are not given a clue, or I should say not using an initial condition, which could also be known as a clue. Not using an initial condition, we don't have like an initial point, or at least we're not using it yet. If we do, given an x and a y, or given a t and a position, or given a time and a starting number of people in the park, given some sort of hint or clue about the amount. So an initial condition, you can think of an amount clue, some sort of x, some sort of y. So general, if we're not using an initial condition, there's going to be some sort of plus c, right? General solutions are going to have a plus c. Now here's what's going to change a little bit in chapter 5. You guys up until this point, if I said something like you were on a quiz, you were on a test, and I said, make sure to see that everything is there. You should be able to go through, go find any indefinite integrals, right? Any indefinite integrals, and just add a plus c at the end and be like, no big deal. And it was fine. But now, if we're going to have x's and y's in the differential equations, just be aware the plus c isn't always going to be just tacked on at the end. It may very well be that it was tacked on at the end, but you had something over here and something over here, and when you try to get y by itself, this can get put into a denominator under a square root, into an ln, or maybe even multiplied in front of an e. And it doesn't get put there, it gets solved and rearranged there. So up until this point, you guys have always been able to just say, plus c. And when you integrate at first, yes, you get plus c. But just to let you know, this plus c will not always be tacked on at the end as the differential equations get harder. But particular solutions, take a general solution and use a clue, right? Use an initial condition, use a clue to find C to plug into y equals f of x. And that's like the test correction that you guys should have done if you missed it on the chapter 4A test. There was a differential equation, a very basic one though. And I gave you a clue. You were supposed to find C, plug it into the equation, and then be done. You were finding the solution, you were finding the y equals just with the C plugged in. Okay? So that's just a quick reminder of terminology. You've actually already seen this whole general in particular. We just haven't really zoomed in on solution and solution to what? A differential equation being like this process. All right. So general, particular, vocab. Let's go do one more. I want you guys just to write down the differential equation. You can name it if you want, but it has a derivative in it, so it automatically is a differential equation since there's a y prime. It's just asking you to check or both? Is it telling you to solve or check or both? Yeah, both. Now, some people would see this and be like, I have to solve and go straight, especially after you guys finish chapter 5. But hold on, didn't they already tell you the solution? Where is it? They already gave it to me. I don't even need to find it. Okay, well, how do we verify it's a solution? We need to find y prime, right? So what is y prime of any constant times x cubed? Don't let the c confuse you. What's the derivative of x cubed?
2x squared.
Bring down the 3.
Oh, 3.
And that c is just a constant, so I can just do it like that, right? Now, if I was to go ahead and take this and take that and plug in, does it work? What is x times 3cx cubed minus 3 times y? Does that end up equaling 0, yes or no? Oops, I didn't put it in there. What was it? It was 3cx. Okay, now does it work? So therefore, check that it's a solution. It's a solution. Now that it's a solution, I don't need to go from here to here. I can use this, because I just figured out that it is right, to find a particular solution. So, particular solution. They better have given me a clue. And did they give me a clue?
Yeah.
Yes. So I could have stored it away in my handy-dandy notebook and brought it out when I needed it, but I need it right now because I already have the solution. I just need to plug and chug. So just reminding you of what this means. This means that you take your original function or your general solution, which is this guy right here, y equals cx cubed, my solution. You plug in your x and you plug in your y and say, okay, y needs to be 2 when x is -3. C is going to end up equaling, any mental mathers out there? Which a negative over a positive is a negative. What's the solution? This? Did you get the vocab? What's the solution? C? Plug it back in. Good. Did you get it? The solution to the differential equation with this initial condition is the y equals who? X cubed.
Yeah, man.
This is the particular solution. We had to find the c, but that was not the solution. The solution was the y equals f of x with the clue plugged in and the c established. Just making you practice the vocab. Kathleen, what's that? Oh, I took my x equals -3 and my y equals 2 and I plugged it into the solution, the general solution. And then -3 cubed is -27. I divided and c equals -2 over 27 that I plugged it in. Is that good? So the solution is the equation of the general function, what came before or what was behind this differential equation. Kind of cool? Kind of okay? But what's this slope field do? The slope field guy, we're just that was all vocab, just kind of introducing you guys to the idea of solutions, differential equations, particular, general. Now let's get into slope field. Okay, section 5.2 comes back to differential equation and solving. Slope fields are an application of differential equations because you guys just told me slopes come from, or slopes are of, baby tangents. And baby tangents, don't the slopes come from or defined by differential equations? Differential equations give us slopes when we plug in. Differential equations give us slopes when we plug in. Now, this is one book's way, and I don't even think it's your book. I found this from a different worksheet, and I appreciated the way they put it. They're saying in order to get a slope field, we can define it. It's not a forever card. It's in yellow just because I think it's important. If you're doing these slope fields and if you forget what they are, how they are, where they are, what they're doing, come back to this box. Don't memorize it. You'll never have to regurgitate it for a forever quiz or for the AP. But it's just the idea, all encompassed. To every point in the domain of F. Every point, but we're only going to do a few. We don't want to infinitely many points, that's not good. Remember a field of poppies. We just need them kind of interspersed. To every point in the domain, even though it could be for every point, we're just going to do some of them. Assign a small piece, a baby tangent, with a slope of, how are you going to find the slope? Using the differential equation. F prime of the xy or dy dx of the xy. Sometimes you need the x and the y, sometimes just the y, sometimes just the x, sometimes both. The slope field at that point will be a small piece of a tangent line with the slope that you found to a curve that passes through. And that curve that passes through, that is referring to the solution to the differential equation. So the solution follows the flow, is my way of saying it. The solution follows the flow. So the y equals f of x, or f of xy. It could be in terms of x and y. But that y equals that guy that we just talked about, how he's called the solution follows the flow. The derivative or the differential equation gives us the slopes. The solution follows the flow. The differential equation defines, identifies, determines the slopes. So if I, as you guys are just kind of writing this down, where's it go? Okay. If you were to look at one of those slope field guys, and if right here there was a baby tangent at 0, 0, what can I tell about the y equals f of x versus what can I tell about the dy dx? Just looking at, for instance, the point 0, 0. The dy dx, I can tell, is supposed to be positive at 0, 0. The dy dx is positive. How do I know that? Well, look at the baby tangent. What's it pointed, or how is it pointed? Okay, the dy dx is going to be a positive number, some sort of positive number, I don't know, but look at that tangent line. Of course the slope is positive. Got him. But y equals f of x, what do I know? Well, he could go through 0, 0. He can go, I mean, he doesn't have to, because he could be anywhere, depending on the shift, depending on the plus c. But he could go through 0, 0. That's about all I know. What if I was to pick another point, and guys, I'm just kind of making up the slope field over here. What if I was to pick the point 1, 1, okay? And what if, all of a sudden, I have one of those flat guys? What if the slope field at 1, 1 is flat? What could I tell about the original solution who's following the flow versus the differential equation? What do I know about the slope? Equals 0, I like the column, because it's flat. When you say a constant, Adam, I think you're thinking a constant function. You're thinking the flow through. And the flow through could be a constant, but hold on, wait a minute. If it was flowing up through 0, 0, and now it's flowing, wait, think about the flow. What could be present here? Yeah, what's it called? The top of a curving thing?
Vertex.
Maximum.
A maximum. It could be a vertex if it's a parabola, but what if it's a sine curve, or what if it's like a cubic function, or what if it's something else, right? Wouldn't it be better to say a possible relative max? Wait, possible relative max, excuse you?
Stop.
Well, what if I was to go to 2, 2, and what if there was another one that had another up? Could it have flowed and then flowed and not had a relative max? But what's the other dilemma? Hey guys, have we found slopes at all the points in between? No. So we see one way over here. No, it's close. way over here at 0, 0, and over here at 1, 1. Couldn't there have been something if we had made these way shorter and way tinier? Isn't it maybe somewhat possible? That maybe right before it could have had a slope that was like that? Right? Couldn't it have been?
Yes.
And couldn't we zoom in even more? And couldn't it? So when you see the slope field, here's something I need you to see. In general, you're going to be following the flow, but to some extent, you can't totally guarantee something like a relative max. We can say possible relative max, maybe. We can say possible point of inflection, maybe. But all we can actually say for sure is that dy dx is equal to 0. Anything we say here is going to be possible. Anything we're going to say here is going to be possible, if I was to take away that point. Because technically, I don't see all the in-between, all the infinitesimally thin other slopes. I'm just kind of making a guess. And if I was to put this in a computer program and they were to give me tons more slopes, I could make a pretty good guess. But even then, technically, I don't know what's coming right before 1, because what is right before 1? 0.9. Nope, what about 0.99? Nope, what about 0.999? Nope, what about 0.9999999? This is like those tables that the AP gives you when they say something like, here's what's going on at 0, and at 1, and at 5, and at 9, and you're like, great, I know what's going on. It's going up. No, maybe it's going, I don't know, maybe it's doing a lot of, they're giving you snapshots. Slope fields are snapshots. But we're going to try to generalize the snapshots to get an idea. So yes, the solution follows the flow. Yes, the derivative determines the slopes. Yes, we can figure out some clues. And then when we're looking at the slopes, we can say dy dx is positive, dy dx is 0, dy dx is positive. But the flow, we can say, I think it can, I think it will, I think it might. The flow is always an approximation. Okay. So, if we were trying to make a slope field, I just made up one. Like, I put a slope there. I didn't actually go to a differential equation and start forming. But you guys in your packet see that we have those little dot grids. Let's open up to those dot grids in the packet. But before we start making them, here's a couple things for you guys to realize. Or a couple things that might help you in writing them down so that you know what I'm doing when I start making slope fields. Because some of you, if you fall asleep or if you're kind of like barely tracking, or if you look up and all of a sudden there's a slope field on the board, you might not know what I have done. Especially those that aren't big mental mathers that didn't love matrices, etc. Because I'm going to be plugging in numbers and I'm going to be using those numbers and I might, oh, right there. You might kind of just get lost if you don't realize, or you don't have something to refer to. Wait a minute, what did she do? Well, here's what I'm going to do. If they ask me to make a slope field, if they have those little dot papers or dot grids, expecting me to make a slope field, here's what I'm going to do. I'm going to go ahead and go to my dy dx. I'm going to make a table of dy dx's. I'm going to plug in certain points, the points that I see the dots at. Let's see. Number 2, I'm going to sketch baby tangents with the approximate slope. I'm going to think of whatever the dy dx is as a rise over a run. And I'm going to pretend.
Yay.
I'm going to think of the dy dx as a rise over a run. Whatever I get when I plug in number 1, I'm going to treat it as a rise over a run in number 2. And sketch a baby tangent line. If it's baby, I can't actually go connecting up to over 1, but I can kind of like pretend dotted line. Ooh, there it is. And you'll see me do that. And then number 3, if after I've made the slope field, if they give me an initial condition, then I'm going to go one step further and I'm going to actually follow the flow. If they give me an initial condition, I'm going to graph that point and then I'm going to follow the flow as best I can. I'm not doing connect the dots. It's not going to be one of those connect the dot pictures where your circle has like edges to it. No. I'm going to follow the flow in a smooth curved fashion, trying to somewhat go between using as a somewhat rough guideline the little baby tangents that I see. I'm going to follow the flow, not connect the dots. It's not going to be this rigid clown with like a little fragmented hexagonal face. It's going to be smooth, it's going to be curved, and it's going to be trying to follow the flow. It's going to be somewhat approximate, and yet somewhat precise as well, because you have a particular point to follow with or from. So I'm going to go ahead and dual page it to get one of these guys up here. And the first guy I have, check it. Is this on your paper? If not, we might skip to another one. Let me get the packet. Some of these are from old notes. X squared. Oh, he's at the very front. But I don't think I actually gave you. Oh, yeah, I do. Example 1. Thank you, thank you. Example 1. dy dx is x squared. Although you guys, do you have the same points I do? Let's just do the points that I have. Can you draw the little dots at the points I have? I'm going -1 to 1, down 1, up 2. Can you draw the little dots? Those are the only ones. I mean, you can keep going if you want, but -1 to 1, down 1, up 2. Those are all the ones I'm going to be doing on the x and y axis and right around that vicinity. Now, as you guys are getting this set up for the ones we're going to do, I'm going to go ahead and do this the long way, this way. But as you guys saw, we have something coming with 35. We don't want to make a table of 35. So you're trying to look for, is there a way of shortcutting this process? Okay, what points do I have? I have the points, there are different ways of doing this. I typically start at 0, 0 because I'm a lazy person and he's easy. And then I usually move either left or right. So I'm going to do maybe like -1, -1. I probably would have done -1, 0, but that's okay. -1, 0, -1, 1, -1, 2. Then I'm going to go ahead and do 0, -1, 0, 1, 0, 2. Wow, we have a lot of points, huh? And then 1, -1, 1, 0, 1, 1, 1, 2. Now, once again, this is the only time I'm going to do this the really long, annoying way. I would for 1. I would for 1. We're trying to look for shortcuts. Okay, where am I plugging these points into? What is going to give me the slopes that I need to make my baby tangents? Who gives me slopes? The derivative, dy dx. Wait, what does this derivative need for me to plug in for all of these points? It only needs an x. Others might need y's. Do you guys see me that needs y's? Ooh, can you guys look at example 2? Just look ahead real fast. Look at that dy dx. Look at example number 2. Dy dx. Doesn't that say x plus y? Don't you need the x and the y to plug in? See it? But this one only needs x for x squared. Oh, sweet. So, if I take the point 0, 0, what happens if I plug in 0 squared? Hey, who else is going to be 0? All the ones with x is 0, right? I might just have it once. Wait, how did I get 0 for all of those guys? Because all of their x's are 0, so if I plug in, wait a minute, what's a 0 slope look like? Little baby tangents, little baby tangents, little baby tangents. Maybe we could have done that without making a huge big table. But are the slopes going to always be the same in vertical lines? No. Only when the differential equation is dependent on x alone. Only when the differential equation is dependent on x alone. Because isn't x equals 0 a vertical line, guys? So all of the slopes on x equals 0, if the differential equation just says give me x, all of those slopes are going to be 0. Hey, so aren't all of the slopes going to be the same for -1 also? What happens if you plug in -1 and square it? Positive 1. Is it always going to be that way? No, but this one it is. Wait, how do I do a positive 1 slope? I thought from a certain point I had to go up 1 over 1 and connect. Well, that ruins my baby tangent idea. So I'm not going to literally connect up 1 over 1. I'm going to visualize up 1 over 1. Let me show you how I think about it. I think about it, let me pretend in gray. I think about it by going up 1 over 1 and then saying, oh, hey, that's up 1 over 1. And then I come back and I say, as I'm visualizing up 1 over 1, I say, haha, there he is. See? I think of up 1 over 1, I think of that, and then I come down and say, haha, slope. So can I think of up 1 over 1, come down, slope. Think of up 1 over 1, approximately, slope. Slope. Do you see what I did? Think up 1 over 1, think of connecting, but only do a little baby sliver of a tangent line, a little baby one. Hey, what's going to be my tangent line at 1? 1 squared is just 1. Oh, so what's going to happen with my slopes? Up 1 over 1. Got him, got him, got him, got him. Keep it parallel. How's it look?
Looks interesting.
But I have a little baby slope field. See?
Yeah.
Did I really need to make a table of all these points?
No.
No. But what made it kind of easy and nice? What was I plugging in for every single point? Just that x. And so what was true if x was the same? It was the same. Right? But let's go ahead and look at the big next page. What's this?
Oh my goodness.
Do you guys see right above it? If we continue doing this for many more points and plot a small piece of tangent line. Oh, this is the bigger version of this. Which one gives you a better picture? The little baby one you just did or the picture that you see here? Yeah, the picture that we see here. But does that kind of give us an idea of maybe how this is behaving? This is a differential equation of a quadratic. Wait a minute, a differential equation of a quadratic.
It's just long.
No, that's the integral. I don't see a line. Do you see a line? Look at this guy. I don't see a line. I see a curve. Wait, what kind of curve seems to follow this flow? A cubic. Why does a cubic make sense? If I integrate, wouldn't I have 1/3 x cubed? A cubic will be following the flow of a quadratic slope field. But now you realize the quadratic is the derivative, and so the cubic is the original. Woo! Okay. Example number 2, though. What are we going to do when all of a sudden we have x's and y's? Now, this guy, I want you guys to put in parentheses and just be like, hey, he's the clue. We'll come back to him later. Come back to him later. Ignore the clue. Just like we ignored it when we solved that test problem. We plugged in the clue later. We solved the derivative differential equation first, I should say. But this one, what's a little bit sad when you guys look at the differential equation? There's an x and a y. Now, I'm not going to make a huge table. But as you guys realize, this has 35 points, and I kind of didn't need to put all the ones I did a second ago. However, I am going to do something just to show you maybe a little bit of an idea. Ready? 0, 0, I'm lazy, I just start there. dy dx, which is y prime, is equal to x plus y. I get my slopes by plugging into that. I'm going to also plug in -1, 1, -2, 2. I'm also going to plug in 1, 0, 0, 1, -1, 2. But I think why I'm choosing these points in particular. Okay. What happens when we plug in 0 plus 0? Remember, x plus y. So what's 0 plus 0? What happens when I plug in -1 plus 1? What happens when I plug in -2 plus 2? How did I figure this out? Well, I've been doing these for a little while. But also, whenever y is equal to -x, won't my differential equation be 0? When will this have zeros? This will have zeros when y is equal to -x. Don't we know what y equals -x looks like? Isn't that like the y equals x line but flipped? So how did I choose this 0, 0, -1, 1, -2, 2? I thought of going y equals -x. So it's also going to go down this way. Hey. So why am I choosing these points? I went over and said, okay, your turn. What happens when you plug in 1 and 0? But, wait, hold on. You guys okay with the up 1 over 1 and then pretend? What else is going to have a slope of 1? Give me 1 second. Where else is going to have a slope of 1? -1, 2. Yeah. And also, 0, 1. And anywhere else, any y equals -x diagonal is going to have the same slope. Okay. So wait, what's something else? Maybe I don't need to plug in any more of those then. I just had to go diagonal. So what's another point I should plug in? How about something like 2, 0? What's going to happen when I plug in 2, 0? What's 2? Guys, are we okay? 2. Yeah, good. 2 plus 0, right, is 2. So 2, 0. Now, it's a little trickier. I have to go up 2 over 1. Remember, think of it as a rise over run, and then connect. It's going to be a little bit steeper. Who else is going to have a slope of 2? All of those guys. And a diagonal y equals negative x squared. Does that make sense? So wait a minute, what about 3, 0? Uh-oh, I don't have enough dots to do this because 3, 0 would be 3, right? Up 1, 2, 3. That's okay, pretend. Okay, I'm a little bit steeper. 4, 0. Uh-oh, I don't know. 1, 2, go backwards. 1, 2, 3, 4 over 1. Remember with lines? And then to some extent, can you just kind of see it's getting steeper and we just kind of pretend?
I just feel like we're doing.
It was 3, 0, 4, 0, 5, 0. So that was a weird drawing. That's just me.
No,
Anyway, do you guys get the idea of forming slope fields?
yes.
What have we not really gotten to practice yet? Matching slope fields. So what I want you guys to do tonight is to finish this one. Ready? And then graph me the other one, and then stop. And then you can go ahead and start playing in homework. Homework is not due until Monday. Is it up on Google Classroom yet? I feel like it's not. I'll double check. But I want you guys to finish graphing slope fields. Maybe you start with matching, but finish graphing and then go play with homework a little bit. The graphing of slope fields, the matching and whatnot, we'll get back to you tomorrow. Bye, guys. Oh, it's in the book. This is us working in class. I have a whole other packet for you to work on. Don't worry. Just do the 2 graphing ones. Unless you want to keep matching. Check tomorrow if you're right. Bye, guys. The homework I'm talking about is the book